Hey guys, welcome back to another video. So in this video, we'll be looking at reaction mechanisms. I got a few questions about reaction mechanisms, and I thought it'd be best to sort of have a video going over what they are, and just having a better idea of what to do uh, when tasked with finding the rate law. So let's start. But let's say the question's asking you, what is the rate law for this reaction? Now, based on just instinct, I'm sure a lot of us would write this. So let's say this is a perfectly legitimate answer, but this isn't actually what we get. Based on experiment, we actually get this. Not too different, but it's substantial enough. Now, the reason why this is correct and this isn't is based on the fact that we aren't given the complete picture. This entire reaction can be broken down into smaller reactions called elementary steps. And these elementary steps add up into a reaction's complete reaction mechanism. Okay, so now let's look at the characteristics for a reaction mechanism. So this reaction mechanism describes this rate law. It describes this rate law. So let's start with finding the rate law for each elementary step. So there are two elementary steps for this reaction mechanism. So for each reaction step, we can find its own rate law. So let's start with the first one. We get that the rate is equal to K1 NO2 F2. And for 2, we get the rate equals K2 NO2 F. So I got these rate laws by using the reactant species and each reaction step's particular rate constant, and then the exponents are nothing but the coefficients of the reactants as well. So each reaction step has its own rate law. Another thing we notice, actually, something very, very interesting. When you add up, that was a bad line. Right, better. If we add up both elementary steps, we actually get the overall reaction. So the way we add each step is we eliminate species that are in the opposite side of each other, and when we add the rest, we get 2NO2 plus F2 yields 2NO2F, and that corresponds with our overall reaction. So like, let's say there's a question where they give you a proposed reaction mechanism for answer choices. Adding all of them up is a good way to know if it's the actual reaction mechanism, because it has to equal the overall reaction. So that's another reaction characteristics that we can use. Another one actually that's quite important is the fact that this fluorine radical is produced in this step and consumed in the second step. So it can actually completely be removed from the rate law. Now, the thing with reaction intermediates, which is what this fluorine radical is, it's a reaction intermediate. It ultimately cannot be in a rate law. So if a rate law has a reaction intermediate like this fluorine radical, it has to be defined in something else. It has to be defined in other active species. Now, the last characteristics we'll look at for reaction mechanism is this slow and fast thing. This is really, really important. Reaction mechanisms need to say if it's slow or fast, because the slow step is something called a rate determining step. This slow step is where we can decide what the overall rate law is for this reaction. So now let's work through some examples. So let's start with this example. We're given the overall reaction here, and they want for us to find what the overall rate law is. So let's first start with finding out what the rate determining step is. So we're giving two elementary steps. This is a fast and this is a slow. Now the slow step is always the rate determining step. Oops. Alright, I'll worry about that later. That is a rate determining step. So let's get the rate law for this rate determining step. So we get rate equals K1 NO2 which is nothing but K1 NO2 squared. So essentially all we need to do is find the rate law for the rate determining step, and we have the overall rate law. But first we need to check that if there are any intermediates in this proposed rate law. NO2 is not an intermediate. Therefore, this is the rate law. That's all there is to it. That's the answer. Now I'm going to work through a little more complicated example, but the overall principles are the same. So this is a little more complicated example, but the question is the same. What is the overall rate law? So let's start with, again, figuring out what the rate determining step is, and that is the slow step. That is the slow step. So let's start by finding the rate law of the slow step. Rate equals K2 N2O2 times H2. This is the overall rate law, but first we need to check if there are any intermediates. Upon consideration, we notice that N2O2 is an intermediate, so we can't have this in our rate law. So what we have to do is define this in terms of the active species, which is nitrogen monoxide and hydrogen. So what we have to do is use the above reaction, the reaction above the slow step, to get what N2O2 is. So I'm gonna write it down right here and explain what it means. So we can essentially define this as, we can do this. K1 NO squared is equal to K minus 1 N2O2. Now the reason I was able to do this is because this is in fast equilibrium, meaning the forward rate and the reverse rate is the same. So that's all I did for this. I equated the rates of the forward and reverse reaction. So I get this. So essentially what I'm able to do is find N2O2 in terms of NO. So what I get is actually K1 NO squared divided by K negative 1 is equal to this. Now what I can do is substitute this as N2O2. Let me just use my eraser. Let's see. I'm just gonna erase. What can I erase? Okay, I can probably erase this, right? So essentially, what we're doing, like I said before, is we're substituting what we know to get it in terms of N2O2. So what I can do is substitute this, right? So the rate is equal to K1 NO squared over K negative 1 times, right, K2 and hydrogen. So this is the overall rate law. Now the obvious question that we'll get after this is, what if there are multiple slow steps? This is a really tricky question, because if there are multiple slow steps, you don't know what the rate determining step is, and it's hard to find the rate law if you don't know what the exact rate determining step is. So all the advice I can give you is, for you to find the correct rate determining step, you need to know what the reaction law is. So an example would be is, like, let's say you have to figure out the reaction law, the rate law, right? Let's say that you had to figure out the rate law already, and then based on this rate law, you can get which one is the rate determining step. Now a more complicated way, or more advanced way to get this, is something called steady state approximation. It's a really complex it's a complex method of finding a rate law with multiple slow steps, and it's not going to be covered in AP, but the essential sort of principle you have to use is the rates of the production and consumption of intermediates are the same, and that's how you sort of approximate a rate law. Alright, that's gonna be it from this video. I hope you guys enjoyed it, and good luck.